Alright guys, so here we have a circuit. It has 3 resistors and 2 batteries. And we're being asked to find the current flowing in the circuit. And we're also being asked to find the difference in potential between 2 specific points on the circuit. In this case, the points are point B and point D. Now we'll start off with the first question. I'm basically going to be doing a check on the direction of the current. What I mean by that is that we have 2 batteries and we know that both of them will produce a current. But one of the batteries kind of has to yield to the other battery. Like one of the batteries has to submit itself to the will of the other battery. Just like a pawn has to submit himself to his king or to his queen. The idea is that one of the batteries is stronger than the other battery, and so that the stronger battery will influence the direction of the current. This battery is 24 volts strong. The other battery is 12 volts strong. 24 is greater than 12. So that means that V2 is the stronger battery. The 24 volt battery is the stronger battery. Because of that, the current will move this way out of that stronger battery, and it will flow into battery V1. Battery V1 will yield to battery V2. And the current is going to be flowing clockwise because of that. So battery V1 is being charged. It's not discharging. That's the positive terminal, that's the negative terminal. That's the positive terminal, that's the negative terminal. Now to actually do the loop rule, I'm going to start at battery V2 and I'm going to go clockwise. I choose to follow the current. So I'm starting with positive 24 volts because I'm leaving from the positive end of the battery. Then I move through R3, and whenever the current flows, the current in general, this is a theory, this is a part of the theory, that the current always flows from high potential to low potential. So we're going from high potential to low potential, and we want to find the change in potential caused because of R3, this resistor. So we're going to do final minus initial, which means we'll get a negative answer. So we're doing minus IR minus the change in potential caused by R3, which is minus I times R, which is 20 ohms, but I'm not going to write the units just to make the loop a little, just to make the process a bit easier to handle. Now I keep going and I move through R1. Again, current flows from high potential to low potential. Final position minus initial position will give me a negative answer, because the potential at this position ends up being lower than the potential here. So negative I times 10 ohms this time. Then I move through V1. Now V1 is being charged, it's not being discharged, which means that V1 is sort of yielding to V2, like I mentioned before. So we're moving from the positive terminal to the negative terminal. The final position is negative, and so because of that we are subtracting 12 volts. So this is minus 12 volts. That's what we write here. Again, I'm not going to write the units just to make it a little easier to solve. Now I move through R2, going that way. Again, current flows from high potential to low potential. So again, that's the final position, that's the initial position. Initially at this position the potential was higher, but as the charges moved that way, at this final position they kind of lost some of that potential because of the resistor. The resistor resists the current. The resistor will slow down the current, basically. So that's why the potential at this final position is lower than the initial potential over here. So that gives us negative I R2, which is negative I times 30 ohms. And now we have kind of completed the circuit. We're back to V2. So basically, Kirchhoff's loop rule says that all the changes in potential caused by each individual component add up to 0 in a complete circuit. So the circuit was complete, it's connected, and because of that current is flowing through, and hence all the changes in potential are equal to 0. As in all the changes in potential caused by the components inside the circuit. That's why there are changes in potential. So now I'm just going to simplify this equation a bit. And now I'm just going to use my calculator. I'm going to do minus 12 divided by negative 60. That gives me 0.2 amperes. Now I'm going to do some erasing. Now for part 2, we're trying to find the difference in potential between point D, this guy, and point B. To do that, the first thing we have to understand is that this equation or difference in potential they've given us tells us that point D is the final position and point B is the initial position. That's how the delta sign works in general. Like delta V, change in velocity, is equal to final velocity minus initial velocity. It's the same thing here, except that we're talking about potential. So this is the change in potential between points D and B, where point B is where we started at and point D is where we arrived at. So VD is basically the same as saying V final minus V initial. So what this thing here is telling us, this piece of information, is that we have to start at point B right over here, and we have to go to point D. We have two ways to go to point D. We can go this way, or we can go this way. You can choose any direction, you'll end up with the same answer at the end. It doesn't matter. I will deliberately choose to go this way because there are technically this way is easier because there are lesser components to go through, but I'm going through the longer way just in case there might be something else to explain. So I start at point B and I go through R1. I need to keep in mind the direction of the current too. I already know the current is going clockwise. That has to sort of be there. So I'm basically following the current. So I'm going from high potential to low potential, which means that again, that's minus the current, which is I, times the R, the resistance, which is 10 ohms. And then I move through the battery, and again I'm moving from the positive terminal of the battery to the negative terminal. Final minus initial. The final is negative, right? Here the battery's potential is supposed to be negative, so we're subtracting 12 volts because of that. So now we move to R2, this resistor. We go from high to low potential. Again, final minus initial. When the protons or the electrons were here, at this point, they had more energy. When they got here to the final point, the electrons lost energy. So that's why the potential at a point further from the initial point is always lesser. Because in this case, the electrons have moved through a resistor, and the resistor is trying to slow them down. And that's the way to explain why current flows from high potential to low potential, because the electrons, or I wouldn't say electrons, I would say the charges are losing kinetic energy or just energy. So that's kind of the proportional to the drop in potential. If they're losing energy, then they're also losing potential. That's what I'm trying to say. Now back to this. So we have negative I times 30 ohms. And now we're finally at point D, so we stop. We don't go any further. We basically completed half a loop, not the full loop. When we completed half the loop to help us find the changes in potential between 2 points, not the change in potential throughout the entire circuit, as the first part of the question asks. Now I'm just going to plug things in and put them into my calculator. Now we have the current from the first part. Whenever this equipment has to be switched over for this and start putting it off the and whenever this feature mutates, search your library for a basic line and put it on the output tab. Oh, this is my second. And that gives me a change in potential of minus 20 volts. So what this is saying is that when I was standing at point B, I had 20 volts more of energy, and as I got to point D, I went through a bunch of brick walls that slowed me down to the point where I lost those 20 volts that I had before. I still have energy here, I just lost some energy because of the brick walls that I had to jump over. I hope this explains the question, and have a good day.